we have been discussing the problem of data inconsistency that may arise out of cooperating processes being executed concurrently. We said that the access to common data, the shared data, has to be done atomically, especially when it's being updated. When we say that it has to be done atomically, means that the entire operation has to be done as an indivisible operation. No other operation is to be permitted when this particular operation is being done. In this context, the concept of critical section was introduced. We gave an algorithm 1 as an implementation, software implementations of the critical section. Let us revisit algorithm 1 to start our discussion. But before that, let me remind you that the basic machine operations like load, store, arithmetic operations, logical operations, etc. are implemented as atomic operations or indivisible operations. Okay, with that assumption, we start our discussion today. Now, this is our algorithm 1 that we gave yesterday. There was it is written in Pascal-like language, as I said, essentially a part of concurrent Pascal. Now, here it's process 0 and process 1 was there, and the critical section, that means the mutual exclusion of critical section, was implemented or was enforced by the variable turn, which can take either 0 value or 1 value. Now, the turn is made 1 by process 0 at the end of the critical section, and turn is made 0 by process 1 at the end of its critical section. The process 0 waits on turn. If it is not equal to 0, that means if it is process 1's turn, then it waits here in a busy wait, okay? Now, then it enters the critical section, makes turn equal to 1, allowing process 1 to enter in the critical section if it is waiting here. Now, this way, here the mutual exclusion was achieved. That means once process 0 is in its critical section, no one else, the process 1, cannot interrupt it, and therefore all the entire operations in this critical section is done as if it's an atomic operation, it's an indivisible operation, okay? So for process 1. But as I said, the problem with this algorithm 1 is that progress. By that, say process 0 is in the remainder section, and the remainder section is taking quite a good amount of time. In the meantime, process 1, naturally its turn equal to 1, it will enter the critical section, make turn equal to 0, will finish the remainder section. Being fast, it will come over to here and it will wait here till process 0 comes, enters it, makes turn equal to 1. Okay. Therefore, you see that strict alterations of process 0 and process 1 takes place, which is not in conformity with our progress requirement, and therefore we should search for a better solution of this critical section problem. The problem with algorithm 1 is this, that algorithm 1 does not keep the track of status of either process 0 or process 1. Okay, and process 0 doesn't keep its status, process 1 doesn't keep its status. Let us try to improve by bringing in another algorithm, say algorithm 2. Okay. Here what is done is that a variable flag, which is an array, okay, 0, 1, that means it is it's a single dimensional array with two elements, array 0 and array 1 of Boolean. That means it can assume array 0 or array 1 can assume either value false or value true. Okay. Here is a process 0, here is a process 1. That flag 0 keeps track of process 0 state, and flag 1 keeps track of process 1's state. Now, if flag 0 is true, which it implies that process 0 is ready to enter its critical section and wants to enter its critical section. Similarly, when flag 1 is true, it implies that process 1 is ready to enter its critical section. Now, say both of them we start with false, that means flag 0 equal to false, flag 1 equal to false. Okay. Then, say flag 0 true, flag 0 is made true, or flag 1 is made true, even they are executed almost simultaneously. Okay. Right. Say flag 0 equal to true and flag 1 true. I'm assuming, say, right at this moment, say that flag 0 is true, okay, and flag 1 is false, right? In that case, say, since flag 1 is false, it enters the critical section, right, executes the critical section, makes flag 0 equal to false, then it enters the remainder section. Now, if process 1 is waiting here, then it sees flag 0 to be false, then it enters this critical section, makes flag 1 false, and then it enters the remainder section. Okay. Now, therefore, this way, say mutual exclusion is once more achieved. That means either flag 0 is equal to true or flag 1 is equal to true. That means either flag 0 equal to false or flag 1 equal to false. That way, that critical section, that mutual exclusion may be achieved. Okay. But let us see the situation. Okay. Let us see the situation that flag 0 is equal to true. Okay. And almost simultaneously flag 1 has been made true. Right. In this case, you see that the process 0 will be waiting for flag 1 to be false, and process 1 will be waiting for flag 0 to be false. Let me repeat once more. Say flag 0 has been made true, and the execution switched from process 0 to process 1 in a single processor system, or in a multiprocessor systems, the flag 1 is made true immediately afterwards. Then you see that both flag 0 and flag 1 is true. In that case, process 0 will be waiting here for flag 1 to become false, and process 1 will be waiting here for flag 0 to become false. Therefore, both of them will be waiting, and none can enter the critical section. And as you see, the progress requirement is immediately violated. Okay, both of them will be waiting is this busy wait situation indefinitely. Now, does the situation improve? Let us see by, say, moving this flag 0 at this point. Okay, say similarly, let us move this one right. Now, say in that case, the situation may turn out to be that, say, flag 0 equal to false in the remainder section. This enters in the critical section, make flag 1 equal to false. Both of them come over here. It sees that flag 1 equal to false. Therefore, it enters, makes flag 0 equal to true. This process 1 sees that flag 0 is equal to false. Therefore, it enters and makes flag 1 to be true, and both of them enter the critical section. Therefore, you see that by interchanging the sequence of these two instructions, that bringing flag 0 over to here, flag 0 equal to true, assigned to true over here, and flag 1 assigned true over to here, that mutual exclusion, that particular criterion is violated immediately. Both of them, both the processes can be in that critical section simultaneously. Okay. Therefore, you see, this is a solution that algorithm 2 is not acceptable, and therefore we should see whether there can be a better software solution which actually solves the problem is there or not. Okay. Now here, we have taken algorithm 3, that we call this the Peterson's algorithm. Okay, here both the flag and the turn, both these variables have been utilized to come to a solution. Okay, let us see what it does. Here the variable flag, once more, it's a single dimensional flag of two elements, array 0, array 1 of Boolean. Array 0, that means flag 0, keeps track of the status of process 0, and flag 1 keeps track of the status of process 1. Similarly, the turn has been kept, the variable. It can assume either a 0 value or a 1 value. If turn equal to 1, as usual, that is process 1's turn to enter, and if turn equal to 0, it is then process 0's turn to enter. Okay. And here is that intersection for process 0. It says it first make true, flag 0 equal to true. That means it says that the status is that he wishes to enter the critical section, right? And it says turn equal to 1. That means it gives the opportunity of process 1 to enter in its critical section. And then it's in this while loop. It says that if flag 1 is true and turn 1 is true, that means if process 1 wants to enter and it is process 1's turn to enter, okay, right, in that case, a process 0 should wait, because in that case, process 1 should enter into the critical section, right? If either flag 1 is false or turn is equal to 0, in either situation, or in both situations that flag 1 falls or turn 1 falls, so both happen simultaneously. In this case, either this happens, that means flag 1 falls, or turn equal to 0, or both of them, that means flag 1 falls and turn is equal to 0, then it enters the critical section. Okay, executes the critical section, and when it exits the critical section, then it makes flag 0 is equal to false. Okay, false is assigned to flag 0, enters the remainder section. That's also true for process 1. That means if flag 0 is false or turn is equal to 1, or both of them happening, then it enters the critical section. On exit from the critical section, flag 1 is made false, and then it enters the remainder section. Now, this solution achieves all the three requirements. That means that mutual exclusion, that progress requirement, and the bounded weight. Okay, let us see. Say this is the way the two processes has been started. The flag 0 has been made false. Okay, flag 1 has been made false, and turn 1 has been assigned 1, say arbitrarily. Then this is parallel begin, pair begin, and pair end. In concurrent Pascal, it says that process P0 and process P1 have been started to be executed simultaneously or concurrently. Okay, then P0 and P1 process starts executing concurrently. Now both of them are false. Flag 0 false, flag 1 false, turn equal to 1 or turn equal to 0. Okay. Now, even if they are executed simultaneously, one value will persist. Let us assume that turn 1 persists. Okay. Then, since turn is equal to 1, that means turn equal to 0 is false, process 1 will immediately enter the critical section. Okay. And process 0 will wait over here. Similar is the situation, okay, when process 0 enters and process 1 waits over to here. Okay, if turns out to be equal to 0, okay, turns out to be equal to 0, then process 0 enters over to here. Therefore, you see, by simply even turn, we can maintain the mutual exclusion of the critical section. That means when process 1 is in its critical section, process 0 will not be in critical section, and if process 0 is in critical section, process 1 will not be in its critical section. Now let us see that progress requirement. Suppose that process 0 has come out of the critical section, it was in the critical section, flag 0 has been made false, and it is in the remainder section, taking a long time in the remainder section itself. Okay. Now, since flag 0 equal to false, if process 1 was waiting here, right, since flag 0 is false, it will immediately enter its critical section. It will make flag 1 false. It will go through that remainder section. If it's fast enough, it will come over to here, make flag 1 true, turn equal to 0, and since flag 0 is still now false, it can enter its critical section. Therefore, it will not get stuck in the entry section or anywhere. Okay, therefore, you see the progress requirement as such is satisfied. Similarly, that bound requirement, that means process 1 or process 0, after it makes a request to enter into the critical section, there is a maximum bound on the number of times the other process can enter its critical section is similarly satisfied. Okay. For example, once more, say flag 0 equal to false, it is in the remainder section, it was waiting over to here, and therefore it can enter the critical sections immediately. Okay. Now, if process 0 is entering its critical section, right, and it is waiting over to here, the moment it comes out of the critical section, the other process can enter the critical section immediately. Therefore, these solutions, that means Peterson's algorithm, this software solution achieves all the three requirements. That means mutual exclusion, then the progress requirement, and the bound requirement, and therefore this can be taken as a software solution of our critical implementation of critical section problem. Right. Now, with little effort, this problem, this algorithm can be extended to more than 2 processes as well. This is a very elegant solution and a simple solution, software solution to the critical section problem. Now, let me stop here so far as that implementations of the critical section by means of software only. As is the case with any other situations, right, while writing programs, the hardware support always make it easy for a software solution. Now, for the critical section implementation problems also, there are hardware instructions that are available which aids in implementing easily the critical section. Let us see what the hardware solutions or what special hardware instructions are there which can be utilized for this purpose. First, let us come to that hardware support in the case of a single processor system, right? What we can do, that in the case of a simple processor system, that since we have interrupt are there and we have interrupt disabling facility, as we have discussed when we had been talking interrupts. Okay, what we can do is that when a process enters its critical section, we disable all interrupts. Now, the situation in the case of a critical section is this: if this particular process is not preempted within its critical section, okay, then naturally the entire critical section can be executed as an indivisible operation. That means it starts executing and finish executing before any other process executes, right? That can be achieved by means of an interrupt disabling. Now, before just entering the critical section, you disable interrupt, enter the critical section. Just before coming out of the critical section, you enable interrupt, okay, and then you enter the remainder section, right? Now, in the case of a single processor system, you see that this disabling and enabling interrupt is not much of a problem. You can disable interrupt and you can enable interrupt to implement the critical section, right? But in the case of multiple processors, this implementation of mutual exclusions by interrupt disabling may turn out to be a problem, because in that case, you will have to inform all the other processors that a process in, say, processor 1 wants to enter the critical section. Therefore, it disables its own interrupt, then sends signals, have to send signals to all of the processors to disable all the interrupts. Okay. Now, after all the interrupts have been disabled, all the other processors should report back that the interrupts have been disabled. Only then this process can enter its critical section. Okay. Now you see that entire process is very time consuming, and a very strict message passing has to be followed for this purpose, and therefore the disabling interrupt for implementing critical section in the case of a multiprocessor system is seldom implemented, right? It can be implemented in the single processor system. I hope you remember that essentially a process is preempted from a processor on a timer interrupt mainly, okay, or it can be by some other very high priority interrupt. Okay. Now, this is one way. See that what can be the other ways. There are special machine instructions that has been devised, okay, to aid in this mutual critical section implementation. One such instruction is a test and set instruction. Okay. Now the function of the test and set instruction I have written in the form of once more a Pascal-like program. Okay, Pascal-like function. Let us see what this function is doing. Okay, what this test and set instruction does. The test and set is a function which returns a value, whatever value this particular variable, the test and set gets, the function name gets. It has one parameter here, okay, this is a variable parameter, name is target, and its value can be Boolean. That means either a true value can be sent, okay, or a false value can be sent as this parameter target, and the value returned by this function is Boolean. Okay. Now, therefore, test and set returns a value Boolean and accepts a parameter which is also a Boolean. Okay, parameter value which is Boolean. Variable means that the parameter passing is by reference. Okay. Now, it does this job that whatever be the target, right? Say whatever be the value of the target. Let us see. Say this is our target. Whatever be the value of the target, it can be either say true or false. If it is true, that value comes as the test and set, and therefore that value is returned. Okay. If it is false, that value comes as test and set, and that value is returned. Okay. And whatever be the situation, that means whether it is true or it is false, right? Whether it is true or it is false, that value comes to test and set, and the target is assigned true. That means whatever be the previous value, after that, this target value turns out to be true. That's the function of this test and set instruction. Okay. I rather suggest that you try to very clearly understand the operations of test and set. Test and set is essentially that whatever be the value, true or false, that comes as test and set, and that value will be returned, and this target will be set to true. And important thing is, this is a indivisible or atomic operation. That means the test and set is an instruction whose equivalent, functional equivalence is given by this function, and it is executed as an atomic operation. That means in between, no other executions of no other operations is permitted. Okay. Both these are done one after the other, okay, and without being interrupted. Let us see how this test and set instruction helps in realizing that critical section. Okay. Here what has been done is, let's say this is a critical section shown in the red, right? the critical section is maintained by a variable which is log. Let's see. Say this is log. Okay. Now the log can have a value either false or true. Okay. Let me assume that this has a value which was a false. Okay. Now this test and set log will do this. The test and set will be assigned f, that means that f false value will be returned because it was false, and this will be made true. Now since the value returned is false, right, it will immediately enter into its critical section. Okay, which means that if original value of the log was f, the test and set will return f, that means false, right? And therefore, since this condition is false, this particular process will enter its critical section and the log will be made true. In the other case, say originally, say the test and set was true, okay, then what will happen, let us remove this one. So what will happen, since original value is true, the moment the test and set log is executed, the true value will be returned, right? And the log will be assigned true, that means it will remain true. Now since it is true, right, then this process will busy wait here. Now just think of the situation that there are more than one processes that are trying to synchronize its operations, okay, that means entering into the critical section in terms of one variable which is log, okay. Now one of these process, say it was started with false, one of this process made it true, say one of the process made it true, and therefore since and entered the critical section. Now the other processes therefore will go checking this that it is true by reading test and set, and if it is true, it will wait on true and keep it true. Okay, therefore it will basically busy wait. All other processes will busy wait over here until and unless the process which entered the critical section by making it true comes out of this critical section by turning this log to be false. In that case, amongst the processes which are waiting here, okay, will find that it is false. One of them will make it, will enter immediately, okay, sensing that it is false, and will make it true immediately. And since this is an indivisible operation, an atomic operation, all other processes will not have any chance to modify the value as the process is changing the value from false to true as it's entering the critical section, right? Now for all other processes, we'll once more wait here, the busy wait here in this intersection, right? Now that is the way that mutual exclusion is satisfied by utilizing test and set instructions, okay? I hope the idea is clear, but just to make the entire thing embed into your mind, let me repeat once more, okay. Say several processes are there, okay, P0, P1 to Pk, all of them have their critical section in terms of a variable which is log, okay. So one of this process, a Pi, could sense it false, make it true, and enter its critical section. Then except Pi, all other processes, P0, P1 to Pk, except Pi, all will be waiting here, okay, by executing test and set. It will execute test and set, sense it is to be true, and set it to be true. Till Pi comes out of this critical section, make this false, okay. The moment it is false, then one of the other processes P0, P1 to Pk except Pi will try to execute the test and set. Since it's an indivisible operation, one of them, say P1 succeeds in executing its test and set, and as it executes in test and set, this false will be made true and P1 will enter its critical section. Others will find it true once more and will be waiting in this entry section. This way, by making this test and set to be an indivisible operation, that mutual exclusion amongst different processes in terms of its critical section can be maintained and is maintained. Okay. Now, test and set is an instruction which are available in many computers, many contemporary computers, and they are utilized to implement critical section. Now, let me give another hardware instruction which we call a swap instruction, okay, that also aids in or supports the implementations of the critical section, okay, and this is a instruction that also is available in many contemporary computers. Here what happens is this, the swap instructions once more, that's an atomic operation, that means indivisible operation, and the effect is this, okay, this is a procedure and not a function, and therefore the values are returned, both the values of A and B will be returned, okay. Let's see that here we have two parameters A and B, both of them are Boolean, okay, and we have a temporary variable which is also Boolean. That means A and B, through these parameters we can send true or false values, and temporary is a local variable which can be used within this procedure, right. What this swap instruction does is that essentially exchanges, okay, interchange the content of location A and location B. A goes to temporary, B goes to A, then temporary goes to A, right. It interchanges the content of two variables A and B, and the entire operation is done as an atomic operation. That's a single instruction whose execution of whose effect is that these two variables, okay, is the values of the two variables are exchanged, right. Now let us see what actually it does, okay. So for example, say this is A, say B, okay, they can be either true or false. Let me assume that say this is true and this is false. Right? At the end of it, of the execution of these instructions, this will turn out to be false and this is turn out to be true because the content will be interchanged. Okay. Now let us see how this instruction can be utilized, okay, to achieve what we call that mutual exclusion, right. Now here we have kept a program. This is the green is our intersection. Here the key is assigned a value true. Key is assumed to be a Boolean variable, right. The critical section is also maintained, okay, in terms of the variable lock. Say the lock initially has been assigned a value of say false, okay, to start with, and the lock is in the shear segment, right, has been assigned a value false. Now after key has been made true, okay, say key is a local variable here. After key has been made true, it has been made true, okay, it exchanges the value of the lock and key, right. Now say the lock was true, okay, if lock is true, you know, in that case the key will also get a value of true and lock will give a value of true. Then you see that this repeat swap, these instructions will go on being executed indefinitely, right? It will go on waiting over to here. It all the time changes true with true. Since key is not equal to false, therefore this repeat instructions will be executed, right? Till say the lock is made false, right? If the lock is false, then the swap instruction will interchange the values. The key will get a value of false, right? Lock will get a value of true, and the moment key is equal to false, this particular process will enter its critical section, right? Now, say there are once more k processes, say P0, P1, Pi, Pk. We start with once more, say the lock, say we start with lock is equal to say false. Okay. Assume that one of these processes, say Pi, first executes these instructions among all of them. Okay, since it's indivisible operation, that key was true, therefore it exchanges with lock, then key turns out to be Pi makes Pi's key false. This is now true, and it finds false, therefore it enters the critical section. Now Pi is in the critical section. All others will find the lock to be true. Okay, sorry, all other processes will execute swap and will execute for all other processes naturally key is true, right? For all other processes, this its own key will be true. Therefore, it will swap true with true, and therefore will essentially busy wait in this repeat until loop. Okay, therefore, except Pi, which has entered the critical section, had make this lock true. Okay, all other processes from P0, P1, except Pi to Pk, will on swap will find that key to be true, because true will be exchanged with true and will be busy wait here. Okay, till Pi comes out of its critical section, makes the locks false, right? In that case, one of the processes, say Pk, will, while executing its entry section, that means swap instruction, will exchange true with false, will get this as false, will make this as true, and can enter its critical section. Therefore, now Pk enters its critical section, and all other processes still go on, will be in its intersection busy looping if they are trying to enter the critical section. Therefore, you see that swap instruction helps in implementing the intersection of a critical section, okay, and that way allows the mutual exclusion to be realized. Okay. Now, for these two hardware instructions, the test and set and the lock, okay, test and set and the swap, these two instructions, which are implemented in either form, in some form or other, in all the contemporary computers, can be taken resort to implement critical sections, right? Now, let us come to introduced another concept, okay, which we call semaphore, right? Now, let us see what is a semaphore. Let us give the definition of a semaphore here. Let's first say that what's the meaning of the semaphore. Semaphore meaning dictionary meaning of semaphore is essentially signaling, right? Many possibly have said that previously, quite long back, in the case of a navy, the people used to send signals by means of different positioning of two flags held in two hands, right? they used to call it semaphoring. That means essentially the meaning of the semaphore is signaling, and that is why whatever has been is being discussed here is called that semaphore, right? Here, in the case of a semaphore, we have a variable which is an integer s, and on this variable we implement two functions. One is called weight s. Previously it used to be called ps, and another is called signal s, used to be called vs, right? That weight s, okay, it says that while s less than is equal to 0, do no operation, okay? And if s is greater than 0, then naturally it comes out of the while loop, it decrements s equal to decrements s, that means s is assigned as s minus 1. Okay. Let me say that what the semaphore operation does. S is an integer and we call it a semaphore variable, right? Two functions on it we define. One is that weight s and is a signal s. Weight is that while s less than equal to 0, it waits here, okay, do no op. Now, if the moment s is greater than 0, it comes out of this while loop and enters this loop, and s is decremented, okay. S is equal to s minus 1. And signal s is that simply s is incremented. Now, in both the situation, that means weight s and signal s, okay, are implemented as a atomic operations. That means they're indivisible operations. Both weight s and signal s are indivisible operations. Previously, as I was telling, that weight s is called termed as ps and signal s is termed as vs, okay. Now let us see just one example that how this semaphore can be used, right? Say, how do I implement mutual exclusion in terms of this semaphore? Okay. What we do is that let us define a semaphore mutex, which stands for mutual exclusion, and assign the value to be 1. Okay. Now here, this is a process which continues indefinitely. Wait mutex. Now since, see, the value of mutex is, say this is mutex is 1, say the initial value of the mutex is 1, then since the value of mutex is 1, you see it is greater than 0, and therefore it comes out of it, decrements it, and goes ahead, okay, goes ahead, okay. Therefore, it decrements the value, it first finds that it is greater than 0, it decrements the value, that which means now mutex turns out to be 0, and it enters the critical section, okay. On entering the critical section, it does whatever it does, and while coming out of the critical section, it signals mutex. Now you see that signals mutex is essentially incrementing s by 1, and therefore it increments to 1 once more, and it is in the remainder section, okay. Now assume once more that there are k processes, okay, say p0, p1, pi, say pk. Now say that pi, on finding mutex to be 1, it decremented it and entered the critical section, right? It is now 0. Now since it is 0, any other process which is waiting on the same mutex, right, the same semaphore variable, cannot enter its critical section because it will wait in its entry section. Okay, since it is less than or equal to 0, it is equal to 0, it will wait over here till it comes out of the critical section and signals it, right? So for example, here you see that say pi comes out of the critical section, signals mutex, by incrementing 1, and it is in the remainder section now, any process from P0 to P1 up to Pk except Pi, anybody waiting on this mutex now can enter by making it 0 into the critical section. And since it is an indivisible operation, that wait is and signals is an indivisible operation, atomic operation, only one of them will succeed in making S to be 0 and entering the critical section, and others cannot enter it, so mutual exclusion is achieved, right? And once more, when it comes out of it, it signals mutex, right? Therefore, you see, by that semaphore, okay, by declaring a variable semaphore, okay, and assigning it the initial value of 1, the mutual exclusion of the critical sections amongst a number of cooperating processes being executed concurrently can be achieved. Now we stop here today. We're continuing the discussions on the semaphore and implementations of the critical section in our next lecture 2.